to look at a quick overview of the definition, notation, and a quick look at graphical representations of mathematical functions. Functions are used throughout mathematics and throughout physics and science to look at relationships where one thing can be connected to another thing. That's extremely vague, but the idea that functions really capture is input-output relationships, where maybe one measurement translates into another measurement or another outcome. A very physical example might be thinking about driving a car. When you step into the driver's seat of a car, you turn on the car and you begin to drive. And if you want the car to move, you have to press down on the gas pedal or the accelerator pedal. And when you press down on the accelerator pedal, there's a function that connects the amount of pressure that you put on the pedal, how hard you push it down, and the amount of gas that makes it into the engine. And you expect the accelerator pedal, when you're driving a car, to always act the same way. So if I push down lightly on the gas, I expect the car to accelerate slowly. It's not going to kind of jerk forward. But if I press down hard on the accelerator pedal, I want the car to accelerate much, much faster. So anytime you press on the accelerator a certain amount, you always expect the same performance or the same acceleration from the car. So in that sense, the function that takes the amount of pressure that you're putting on the pedal and turns that into an amount of gas that makes it into the engine, or amount of fuel that makes it into the engine, always gives rise to the same behaviors. So functions are transformations which take in elements or convert elements from an input set and then transform those into elements of an output set. The definition of a function, the thing that makes it, that we use to attach this word function to it, requires dependability. It requires that the transformation be predictable or reliable enough so that any input that's given to the function always transforms into the same output. So in the gas pedal example, the amount that we push on the pedal, the pressure that we push on the pedal, should always give rise to the same acceleration in the car. The car should always respond in the same way. If you touch lightly on the accelerator pedal, you expect a little acceleration. And if you push the pedal to the floor, you expect the car to accelerate as fast as it possibly can. Okay, so that's kind of an example of a function or an idea where functions could be applied that don't translate naturally into numerical functions, which are the ones that we study most often in mathematics classes. All right, so functions are transformations. They take inputs, turn them into outputs, and they're dependable. If you feed a function the same input multiple times, that function is going to give you the same output every time it gets the same input. Okay? So as a couple of examples I'd like to look at, we're going to look at some numerical functions where the inputs and the outputs are both belong to sets of numbers. And to do that, I want to introduce a couple of different pieces of notation that help us talk about functions and describe what they're doing. Okay, so the first piece of notation is going to give us a way to look at what the input and the output sets of a function are. And then we'll come up with some notation that tells us how to define a function and how to transform the inputs into outputs using real numbered examples. Okay. For these examples, I'm going to use f as a label for my function. So the first piece of notation we use describes the input set and the output set of a function. And we have special terms for those. And in the examples that I'm going to use, I'm just going to use real numbers as an example for an input set and an output set. And I'm going to notate that with a capital R with a double vertical line. This is kind of a standard shorthand notation in mathematics for the set of all real numbers. So I want to take a function whose inputs are real numbers and outputs are real numbers. When you see notation like this, it describes the input set and the output set. The formal terms for these, the input set is called the domain of the function, and the output set is called the codomain of the function. All right? And there's another word that we attach to the output set of the function that's a little bit more specific or more careful in a certain sense than codomain. That's called the range of the function. And that's going to be something that's slightly different. So for the codomain, let me specify this as the kind of output. Okay? So we're going to have a function. This is going to transform things from the input set, which are going to be real numbers for our examples, and then it gives back numbers from the output set. Okay? And let's start with a really, really simple example, about as simple as you could possibly hope for. And what I want to use as an example, first I'll describe it in words, and then I'll show you another piece of notation which will allow us to write it down and manipulate it formally. So I want to think about a function which just leaves its input alone. So the output of a function is exactly the same as the input. Sometimes this might be called the identity function. So what I want is an input to be turned into or left alone, to be kept as itself. So to kind of link that to this label f, we have something called argument notation. So our first example is going to be the identity function. Okay? And what I'm going to do is I'm going to write down a short set of symbols which links what I'm talking about to the function. So f was the name of the function, its label. I'm going to write down f of x, and this set of symbols is going to stand for the output of the function. This is the output of this function f when x is an input. Okay? And the reason I call this argument notation is this piece right here is called the argument of the function. Okay? So the identity function, what I need to do to define that for you, or to give you a way to work with that mathematically, is to tell you how to get the output value from the input value. Now the identity function is very, very simple. It's just a function that leaves the input alone. So what we want is we want the output of the function to be equal to the input. Okay? So when you see a statement like this, something where you've got f of x on one side of an equation and some formula on the other side, you should think of that as a definition of f. Okay? So this tells you what to do, how to get from the input of the function to the output of the function. So I read this argument notation, f of x is equal to x. So f of x is the output value. This side gives me a formula or an expression that I can evaluate to get values of f out. Right? So for this simple example, if you wanted to use this, suppose you wanted to know what would the output value be for a certain input. So what is the value of the identity function if I use the input of 2? This is, again, a really, really simple example, but the way that this notation works, it allows us to get those values. So f of 2, I take the 2, I put it into this formula, and I evaluate it. And as you might expect, since this function just leaves everything alone, it just returns the input, the output for this identity function with an input of 2 is also 2. Right? So let's try to use this notation in a more complicated example. Again, not overly complicated, but something where the function's at least doing something. And here I'm going to reuse this label f. It's pretty common to use this again and again in lots and lots of different problems. And that just avoids us from having to think about lots of different things. If you see a label f somewhere, it's a pretty good guess that it's referring to some type of function. Okay, so how about we talk about maybe a tripling function. So what I have in mind here is a function that triples the value of the input. Okay? So I'll again use x to stand in for the input of this function, and I'd like to figure out a formula that will triple the value of x. And here we arrive at something that's kind of interesting. There might be more than one way to write down a formula for a function. So if I want to triple the value of x, one way to do that would be to multiply x by 3. Do 3 times x for my tripling function. Another way to get the value of this tripling function would be to add x to itself 3 times. So f of x is equal to x plus x plus x. Both of these formulas are going to do the same thing. They're going to induce the same transformation from the input number to the output number. So they would both be reasonable formulas to help us define the value of f. Okay? So we can use either of these. Of course, they're equal to one another, so it's not really surprising, but let's use this function notation again. So if we have this tripling function, we might ask the question, what's the value of the function when the input is 2? We'll use the same input as we used in the previous example. So what's the value of our tripling function when x is equal to 2? So we plug in 2 to the argument notation, and then we substitute 2 into the expression for the function, the formula that defines what the function does. We take that 2 and we multiply it by 3. And what we get is 6. 2 times 3 is equal to 6. So that's not really surprising, but what's important here is that you understand this notation kind of reuses some of the notation you've already used in mathematics. And you need to recognize how this notation is being used in context. So in this equation that I've written right here, on the left-hand side, I'm interpreting this as function argument notation. I read f of 2 being the value of this tripling function when the input is 2. On the right side, I've written almost an identical string of symbols. I've written 3 parenthesis 2 close parenthesis. But here, what I was doing was plugging in 2 as the input to this formula, 3 times 2. So even though the left-hand side has f right next to a set of parentheses and the right-hand side has 3 right next to a set of parentheses, this doesn't tell us that f is equal to 3 because we're using the parentheses in a different way on each side of the equation. And this kind of thing can be difficult to get your head around. But context, the kind of story around when you're solving a mathematical problem, has a big impact on how things are used and how things are interpreted. So if you're dealing with functions and you're using this function argument notation, it's not the same as multiplication. To help clear it up, maybe I should write in a multiplication symbol here. 3 times 2 rather than f of 2. Okay? All right. So that's kind of the basic idea behind functions. We have input-output notation or domain codomain notation to tell us the kinds of things that are going in and the kinds of things that are coming out. And then we have argument notation. This gives us a quick way, a short set of symbols that stand in for the value of the function at certain inputs. And then if we have a formula that tells us what the function does, we have a way from getting from the inputs of the function to the corresponding output. Okay. Next, what I'd like to do is I'd like to look at graphical representations of functions. We'll draw graphs of a few functions, and we'll look at what the definition of a function tells us about how it looks graphically. Right? And this will lead us to something called the vertical line test, which you may have heard about before. Okay, so I've drawn up three sets of Cartesian coordinate axes. I've used X to stand for the horizontal axis and Y to stand for the vertical axis. I've done that in three different cases. And what I'd like to do is I'd like to draw for you three graphs. Two of those graphs are going to be graphs of functions, and one of those is going to be a graph of a mathematical equation, which is not actually going to be a function. Okay? So what I've done is I've used argument notation here to define two functions, and maybe it's a bad choice to call them both f. I'll call the second one g. Okay, so interpret the left-hand side as argument notation and the right-hand side as the formula that tells us how to turn an input into an output. So the f here is going back to that identity function that we used first. F of x is going to be given by x, so the output is the same as the input. And here I'm going to say that g of x is equal to x squared minus 1. This is going to be a parabola, and we'll graph this as well. Okay, so when you graph a function, the most standard thing to do is to assign the output values to the vertical coordinate. When you draw things in Cartesian coordinate systems, each point is specified or linked to a value on the x-axis and a value on the y-axis. Say this is the value A and this is the value B. We would write down the coordinates of this point by describing the x-coordinate first and the y-coordinate second. Okay. So when we try to draw a graph of the function, what we want to do is color or shade all of the points where we have input-output connections. All right? So we're going to link the inputs and the outputs by coloring in a path or a curve which captures all of those ideas. So what we actually do is we look at assigning the y values to the function. Okay? So when you graph a function, you actually find all points where y is equal to f of x. Okay? So you find all points where this equation is true. Right? That's your job when you're trying to graph a function. So if I have f of x is equal to x, I want to graph the equation y is equal to f of x. So using this formula, I want to know when y is equal to x. That's what I need to graph. All the points where this is a true statement, and I don't want to color in any points where that's not true. Okay? So I would expect that you've done a wide amount of graphing in the past. So I'm going to kind of go through the actual graphing process very, very quickly. If I think about this, I can think about this as a line. It's a line in slope-intercept form. The slope is 1, the intercept is 0. And what we end up with is a diagonal line with a slope of 1. That's the line. Y is equal to x. And what we're drawing is an instance of all the points x, f of x. And since f of x is equal to x and we're graphing y is equal to f of x, we end up graphing all the points where y is equal to x. Okay, so that's a graph of the function f of x is equal to x. In the second case, get rid of all this stuff. If I want to graph the function x squared minus 1, again, what I want to do is I want to look at the places where the y value is the same as the function value. So I want y equals g of x in this case, or y equals x squared minus 1. Now, this is a little bit more complicated to graph. If you're familiar with using parabolas, one way to graph this is to be able to factor this polynomial, this quadratic, and find its roots. So this guy factors into x plus 1, x minus 1. And if I want to find the places where this is true and y is equal to 0, the factored form tells me that x equals negative 1 and x equals positive 1 are roots of this polynomial. Okay? Another way to think of this is as a vertical shift of the regular parabola x squared. So a rough graph of this function might look like this. Okay? This would be 1, 0. This would be negative 1, 0. Be the locations of those roots. And then this point right here would be 0, minus 1. That's 3 points on that parabola, on that quadratic graph. Okay? All right, so now we have two graphs down, and I want to show you really quickly the property of functions that we can look at or see from their graphical representation. And the key is this idea of a function being dependable. A function has to be able to take an input and always return a unique output, a single thing that that input turns into. So when you look at the graph of a function, different inputs correspond to different locations on the horizontal axis. So different values of x are different places on the horizontal axis here and on the horizontal axis here. And if we have a function, then every one of those inputs, every one of those x locations can have at most one output, a single output. Which means that if I look at a single x location, say right there, there can only be one place that the function, the graph of our function lines up with that input. So if I draw a vertical line that looks at all the y values at that same x value, if I draw a vertical line, it can only pass through the curve, the graph of the function, once. If there were multiple intersections between that vertical line and the graph, we wouldn't have a function. It wouldn't satisfy the definition of a function. So this idea is turned into, or called, the vertical line test. And you can use this graphical property to test whether a certain function or relationship actually defines a function. Okay? So what you do to use the vertical line test is you graph a mathematical equation, and if that mathematical equation passes the vertical line test, so that at every single x value, there is at most one intersection with the curve that you've drawn, you can say that that curve actually defines a function which connects inputs to outputs. So to kind of build on this, what I'd like to do is, I'd like to do one more example where the thing that I'm going to draw at first is not going to be a function, but I'll show you how we can kind of chop it into pieces and turn it into a function. So I'd like to look at a graph of the equation for x squared plus y squared is equal to 1. This is not going to define a single function. All right? If we look at all the xy points that make this true, it turns out that they describe a circle. They describe a circle with radius 1. And we can see that if we connect it to the Pythagorean theorem. If I draw a triangle, and I make it a right triangle, I call the bottom side x, the vertical side y, and I look at the hypotenuse, I know that the hypotenuse is going to satisfy the relationship x squared plus y squared is equal to h squared. Okay? And if I force this hypotenuse to be length 1, then I get a family of triangles that all have the same length hypotenuse. Okay? And if I look at all the different places that I can place that hypotenuse of 1, they're going to describe a circle. Okay? So you start out, put your hypotenuse flat on the x-axis, x equals 1, y equals 0. That gives you 1 point on the curve. Maybe put the thing at 45 degrees. This is still going to be length 1. That gives you another point on the circle. And you keep moving that hypotenuse all the way around. Sometimes you draw the triangle in a different way. Down here, this is my x-coordinate, this is my y-coordinate. This hypotenuse is 1. And you go all the way around. So if we only shade the places where the coordinate point xy satisfies x squared plus y squared is equal to 1, we're going to stay on this unit circle. Okay? And if we now look at this picture, we can ask the question, does this equation satisfy or define a function? And the answer is no. If I look at this x value right here, which might be a half, what I see is that if I draw a vertical line at that location, it intersects this curve twice. So there's no way that this whole curve can define a single function of x, because if I plug in x equals a half, I get two possible outputs. It doesn't have the dependability that a function requires. Okay? And this feature actually comes out of the algebra as well. If I wanted to manipulate this equation to write it the way that we wrote our previous examples that were functions, if I wanted to solve this for y, I'll find that there are two separate solutions, two different sets of y values that can satisfy this equation. So if we look at this, let's bring the x squared to the right-hand side of the equation by subtracting it from both sides. And then to finish solving for y, we need to take the square root. And what's interesting here is that square and square root, they aren't perfect inverses of one another. They don't cancel each other out. So we often consider two branches, a positive square root and a negative square root, if we're trying to find the values of y that might satisfy this relationship. And that gives us two parts of this curve. The upper part and the lower part. And if I restrict my attention to one side or the other, they do satisfy this vertical line test. So they would define functions. Okay? So the circle, the unit circle here, has two pieces. If I want to think of it as a function, I need to think of it as two different parts. an upper circle and a lower circle, if I want to think of it as a function of x. Okay, so that's a basic overview of the definition of a function, argument notation, and a look at how you graph functions and the idea of the vertical line test, which allows us to test, if we draw a picture of a mathematical equation, to see if that equation defines a function globally. We've also kind of looked at the ability to maybe split a function into parts, or excuse me, split an equation into parts and use different parts to define different functions. Okay? And that completes this video.